That's exactly right. Thank you, Charles. It's a great pleasure to be here. And as Charles has said, I'm talking about CoTHH and calculations. And before I tell you anything about, well, we mostly know about what the word calculations mean, but before I tell you about what CoTHH means, I'd like to start by saying that the work that I'll talk about today is joint with Tina Gerhardt, Amelia Hogenhaven, Brooke Shipley, and Stephanie Ziegenhagen. So thanks to them. So as I said, calculations is a relatively familiar term for most of us, but CoTHH I expect is not. And so the way that this talk is going to go is I'm first going to give you a little bit of ideas and context about CoTHH very briefly, tell you what it is, and then tell you a little bit about the calculations. So that's the overall outline. So CoTHH. So right off the bat, I should tell you that CoTHH stands for topological co-Hochschild homology. Obviously. And for reasons of aesthetic beauty, I believe that we put the co in front of the THH. So what can I tell you about CoTHH? So first of all, the word CoTHH should remind you of THH, which is probably a much more familiar object to most of you, topological Hochschild homology. And topological co-Hochschild homology is like do topological Hochschild homology, but for co-algebras. So that's the basic idea is you want to take the ideas of topological Hochschild homology and do them for co-algebras. So it's an invariant of co-algebras. And as I said, it's dual to topological Hochschild homology. So just as topological Hochschild homology, you should think of it as the topologicalization of something called Hochschild homology, which is an invariant of algebras. There's actually a classical invariant of co-algebras called co-Hochschild homology, which was studied in particular by Doi in the 80s in a paper called Homological Co-algebra. So this is a classical invariant of co-algebras. I guess I'm going to call them co-algebras, even though really I maybe mean co-rings in this case, because co-algebras sounds better. And then topological co-Hochschild homology is the topologicalization of co-Hochschild homology in much the same way that topological Hochschild homology is the topologicalization of Hochschild homology. So then CoTHH is the topological version. And the CoTHH, for example, was defined by Hess and Shipley. And there are maybe precursors to CoTHH in certain cases due to Farinati and Solitar and previous work of Hess. So this is the basic idea is that we're going to take the dual of Hochschild homology and then step it up to a topological version. So maybe I should give you some context for why you might think about this, and in particular, like co-algebras. Like we don't really think about co-algebras nearly as much as we think about algebras. And so what would be an example of a kind of co-algebra you might think of? Well, let's let X be a space. Here's a co-algebra. I can take the diagonal map from X to itself, and I'm going to make this be my co-multiplication. So this is my co-multiplication for a co-algebra. So this makes my space is going to be a co-algebra. And then, in fact, you can take, maybe let's work in spectra. So we'll take its suspension spectrum. And we can take CoTHH of the suspension spectrum of X. So now my X is a co-algebra, my suspension spectrum is a co-algebra spectrum. And so whatever this topological CoTHH shield homology is, I'm going to apply it to this guy. And the claim is that work of Malkovich tells us that this is the same thing as the suspension spectrum of the free loop space of X. So let me highlight that this is work of Malkovich. He was not thinking of this left-hand side as CoTHH when he was writing this down, but this comes out of some recent work of his. Hess and Shipley also have some related proofs along these lines as well. So, and then, in fact, many of you will recognize that the free loop space, the suspension spectrum of the free loop space, this is THH. Oh, I'm sorry, I need simply connected here. So that this is THH of the suspension spectrum of the based loop space, like this. So this is perhaps, this particular example tells us that in certain cases, in this simply connected case, CoTHH of the coalgebra structure is telling us about the free loop space, and it's also telling us about THH of the based loop space. And so one way to think about CoTHH is it's another way of accessing familiar objects. So that's one way to think about this topological CoTHH shield homology, is that in particular it's giving us another point of access for things that we're interested in. For example, if you're interested in, say, the Waldhausen A theory of my space X, then there's a trace map to this guy. In the case where X is simply connected, the Waldhausen A theory by work of Hess and Shipley, in the case where we're not simply connected, can be calculated in terms of the K-theory of comodules over the suspension spectrum. And so maybe you should be thinking, taking seriously this coalgebra structure is the kind of thing that might give us access to Waldhausen A theory in these non-simply connected type cases. So this is just a little bit of context to tell you that CoTHH, it should be familiar in the sense that it's a dual to a familiar object, but it's also actually, in some cases, coinciding with this familiar object and giving us another way of getting at that object and thinking about it. And perhaps we'll come back to this point later on in the talk. OK, so this is sort of our context. And I've sort of said CoTHH a lot, but I haven't really told you what it is, except that it's dual. So let's make that actually quite precise, and I will define what I mean by CoTHH of a coalgebra. And to do that, as I said, it's dual to THH, so I'm going to recall the definition of THH, and then I'm going to dualize. So the context that I'd like to work in is I'd like to work in some sort of sufficiently nice monoidal model category. So let's say that. So let's say C is a nice monoidal model category. And THH is going to be an invariant of algebras in C. So if I have an algebra A in C, so it's an algebra, so that means it gets to have a multiplication and it gets to have a unit. And what I'm going to do is I'm going to build the THH of A from the data of the multiplication and the unit. And I'll build it by building a simplicial thing and then taking its geometric realization. So let's say that. All right, so we'll define our simplicial object, THH dot. Of A. Now I'm confused about my upper and lower dots. I did want that one to be a lower dot. Oh, good. All right, so what does it look like? Well, at level n, THH n of A, this is going to be A tensor with itself. I suppose tensor is the name of my monoidal structure in my nice monoidal model category. It's going to be A tensor with itself n plus 1 times. And if it's going to be a simplicial gadget, I have to tell you about the face maps and the degeneracy maps. And the face maps going down are going to be multiply. So these are going to be multiply two adjacent copies of A next to each other, right? And then I'll get down to one less. The only tricky part is that when I get down to the last face map, I've got to wrap round this back one to the front one and then multiply. So the last one is twist, then multiply. And the degeneracy maps, are going to be given by, well, if I want to get from n plus 1 copies of A to n plus 2 copies of A, what will I do? I'll say, hey, I can stick a unit in sort of any of these possible spots where I've got a tensor here. And then I have a unit map that goes from my unit object to A, and so I can use those unit maps to get myself up one level. So these are going to be the unit map. Right? So now this will give me a simplicial object, THH dot, and then what I can do is take its geometric realization. So once I've got a simplicial gadget, I'll take its geometric realization, and I'll call that THH of A with no dots. So then we'll say THH of A is, well, the geometric realization of THH of A. You might complain that I just said I had some sort of nice monoidal model category, and what does geometric realization mean here? Perhaps what I really mean is the homotopy colimit over delta of THH dot of A, and then maybe I require some niceness conditions on my simplicial guide, maybe some really cofibrancy to make sure that those are actually the same. But in general, I can define this homotopy colimit, and in good cases, it's going to be the geometric realization, which is the thing that you sort of already wanted it to be anyways. So this is crash course in THH, how to define it. And so if we want to do CoTHH for a coalgebra, what we're really going to do is we're going to just dualize this whole picture. So to do CoTHH, we just dualize everything. OK, so let's be explicit about that. So CoTHH, what are we going to do? Well, we're going to say, suppose C in script C, in our same nice monoidal model category, this is a coalgebra. So what does this mean? This means that C has co-multiplication, which we'll call delta, and that C has a co-unit map. I guess I'm going to call my unit S, because I'm a homotopy theorist. So we have a co-unit map from C to S. And so this is our it satisfies some compatibility conditions and whatnot. So this is our coalgebra structure. And using the coalgebra structure, we can define not a simplicial object, but now a cosimplicial object, just by dualizing our previous picture. So we'll define CoTHH, maybe it's a small c, CoTHH upper dot of C. So this is a cosimplicial object. And at level n, CoTHH n of C, well, just as it's before, it's going to be a bunch of tensor copies of C with itself, n plus 1 of them, in fact. And now I'm supposed to have co-face maps and co-degeneracy maps, and they're going to be dual to the face maps and degeneracy maps I had before. So the co-face maps, I'll write it here. And I'm going to be precise about exactly what these are, mostly because I want to be quite clear about what happens with this twist at the end, which is sort of the part that might not be directly obvious. So the co-face maps are going to be coming from our co-multiplication, as I said. And then plus there's a twist at the end. And what does this actually mean? This means that the kth co-face map is given by, well, what do I do? On this guy, so the co-face map is going to have to go up now instead of down. That's how dualizing works. So I have to have a bunch of copies of the identity, I guess k of them, and then now I'm supposed to do my delta, my co-multiplication. So somewhere in the middle here, I co-multiply up, and then I do however many copies I had left of the identity to get myself all the way to the n. I guess that's n minus k. Right, so this is for all of the coface maps except the very last one. So this is for k between 0 and n. And then for the last one, what am I going to do? I'm going to first co-multiply. So I do the co-multiplication and then the identity however many times I've got left, which I guess is n times here. And then I have to twist round. I twist my first copy and all the rest of the copies around. So this is a twist of C with, I suppose that's n plus 1 other copies of C. So just to be clear about how the twist comes up when you're dealing with these coface maps in the dual case. So you should think the twisting has to happen after co-multiplying here versus like before, if you were just thinking about algebras, you have to twist and then multiply. But now you have to co-multiply and then twist. All right, so that's the co-multiplication. Those are giving me the coface maps. Really, you should just think if I can co-multiply, then I can coface. And if I can get my codegeneracies from the co-unit, how do they work? Well, these ones are much more straightforward because there was no twist. So the kth codegeneracy map is going to be do the identity a whole bunch of times, I guess k plus 1 times, and then do the co-unit, and then do the identity however many times you had left. I guess n minus k. Right? So if I just stick in the co-unit here, now I've turned one of my copies of C into a copy of S, and so I can forget about it. Right? So this is the definition of the CoTHH cosimplicial gadget. And then to define CoTHH as an object in my monoidal model category, I have to, well, do the opposite of geometrically realizing it. So CoTHH of C with no dots, right? This should be, well, maybe the direct dual here is I should take the homotopy limit over delta of CoTHH upper dot, right? And then under nice conditions, this should be the totalization of this cosimplicial object. So maybe to make this statement true that these are equal or equivalent, I need a redefibrancy condition, say, on C or on CoTHH of C. And in order to make this a homotopically meaningful statement, I have to also should assume perhaps that C is cofibrant to get homotopy invariance. So I'm not giving you a whole lot of details about what's going on at the model categorical level, but there are some things that you do have to be thinking about there. So C cofibrant is going to give us homotopy invariance. I guess invariance under weak equivalence in the monoidal model category context. But as you can tell, I'm secretly thinking about topology. So this is it. This is our CoTHH. And I should point out that the redefibrancy condition that you need to get this here, this is like trickier than ready cofibrancy that came up in the dual case. It's maybe less obvious that you actually have that kind of fibrancy in all cases, although we show that you do in a variety of interesting ones. So I should say this does actually generalize the work of Doi and of Farinati Solitar about particular cases of this. And I also should say one thing that you should observe here is that if you've spent any time thinking about these things, you'll know that totalization is a less happy functor than geometric realization, right? Geometric realization is a very pleasant functor, and we like to think it sort of commutes with the things that we want it to commute with, and totalization does not have that behavior. So this is sort of up until the point where I took totalizations, this was a sort of a strict, very straightforward dual of what was happening in the algebra case. But now I've taken totalizations, and you should be thinking totalization means that something something difficult could be happening here. So it's harder to get access to the CoTHH ones in certain cases because of the totalization versus the geometric realization conductor. All right. So any questions before I move on to the next stage? All right. So maybe I said we're working in some sort of very generic monoidal model category that I wasn't very clear about. So let me tell you some examples of Cs that you might think about. So example Cs. Well, one is you could think about like just coalgebras over a field or something. Chain complexes there. So coalgebras over a field. And this is really the classical case with Doi. You might think about DG coalgebras. And maybe over a field again. And there's a lot of work here by Hess, Parent, and Scott. So there's a case of interest there. And then maybe another very obvious one that's secretly in the back of my mind here is you might think about something like coalgebra spectra, and more about that later. So these are the kinds of model categories that I sort of have in mind. And I should say that maybe the word topological should really only apply to these latter two. Maybe if I'm doing classical things, it really should just be CoHH and not CoTHH. OK. So that's the what is CoTHH section of this talk. And then the next section of this talk is about some calculational things you might say about this. So, OK, so let's see. So I want to focus on DG coalgebras and on spectra, but let's think about DG coalgebras first. So, and let's think back to the dual situation to sort of give ourselves some perspective on what's going on. So if we think about Hochschild homology or topological Hochschild homology, one sort of nice, I don't know if it's strictly calculationable, but one sort of nice identifying result about Hochschild homology and topological Hochschild homology is the Hochschild constant Rosenberg theorem, which is telling you that you can identify Hochschild homology with derivations in certain cases. So let's draw a little line here. And let's say the Hochschild constant Rosenberg theorem. This is saying that we can identify HH with derivations. So it's giving us maybe a calculational way to think about what is Hochschild homology calculating. There's a topological version, as I alluded to. The topological version is due to McCarthy and Manasian. And the topological version identifies THH of an algebra spectrum with topological Andre-Quillin homology. So this is the topological analog of the HKR theorem. And I'm not going to prove the dual HKR theorem today, but what I'd like to do is, if we think about, actually in both of these cases, how does the proof go? Well, the proof goes, think about what happens to polynomial algebras. So start by thinking about, if I want to understand something about Hochschild homology or topological Hochschild homology of algebras, I should start by thinking about the very simplest kinds of algebras I can come up with, which are polynomial algebras, and understand what happens there, and then see if I can bootstrap my way up to more general kinds of algebras by understanding this simple case. And so this kind of idea led us to believe that maybe what we should do is start trying to understand CoTHH by thinking about the simplest kinds of coalgebras. And so that's what I'm going to tell you about in the calculational section, is something about what happens when you have simple coalgebras. What can you do for CoTHH there? So over here, we're starting with free polynomial algebras on stuff. So if we start with polynomial algebras on some generators, well, how do we want to think about these if we're going to like turn our things around into coalgebras? We should think about these as these are the free commutative, or maybe graded commutative. These are the free commutative algebras on some generators. And so if I want to think about dualizing this, then what I really need to be considering for the input of my CoTHH is free co-commutative coalgebras, or maybe co-free co-commutative coalgebras. Right? There's a lot of co's, so we should think about we'll write them all down, co-free co-commutative coalgebras. And I don't know about the rest of you, but before I started thinking about these kinds of ideas, I had never really thought about co-free co-commutative coalgebras and what that actually meant and how do they look and how do you build them. And in general, in fact, thinking about coalgebras is quite difficult. I feel like our brains have been trained through many, many years of practice to think about algebras and not about coalgebras. But it turns out that you're in luck because secretly you probably actually knew a little bit about these co-free co-commutative coalgebras. So maybe we'll let SC be this will be the co-free co-commutative coalgebra functor. So S is for symmetric, and C is for co-commutative coalgebra functor. And secretly, if we're working in sort of in a graded case, then in fact, like if I take the output of these guys are identified with the underlying coalgebra structures on the classical Hopf algebras that you've thought about. So these are giving you things like divided power. So I kind of want to say divided power algebras because like that's what we always call that Hopf algebra is the divided power algebra. But I mean the coalgebra structure that comes along with the divided power algebra to make it a classical Hopf algebra. So I mean, I guess I'm still going to write divided power algebra, but you should secretly think that maybe I mean the coalgebra coming from the divided power algebra. So we'll write that in parentheses, coalgebra coming from. And so this is in the case where say let's work over a field of characteristic not equal to 2 because that makes life a little simpler. This is in the case where my generators are going to be in even degrees. And in the case where my generators are in odd degrees, I'm going to be looking at the underlying coalgebra structure of the exterior algebra. So this is all right? Coalgebras are sort of a mysterious bunch of things and we don't really know about them. But as just topologists, we do actually think about these Hopf algebras. They come up quite a bit. And so we're not sort of totally at a loss to try and understand these objects. So let me tell you sort of, this is not the HKR theorems, but maybe the beginning of what you might expect from an approach to the HKR theorems. That was a lot of hedging, But it's you know, that's how it goes. So let's say in the DG case, so maybe our category C is going to be DG modules over some field, maybe, then what we can do is we can prove that, well, we can identify what happens when you take the CoTHH of one of these co-free co-commutative coalgebras. So let's say so K is a field. Let me be precise. So for X in bounded DG modules over K, there's a quasi-isomorphism from the CoTHH of the co-free, co-commutative, co-algebra on X, this is this SC of X, to the co-free, co-commutative, co-algebra on X itself, tensor with the co-free, co-commutative, co-algebra on the shift of X. So you should think about this as if I were uncoing everything, if I were just doing some sort of Hochschild homology or topological Hochschild homology, then the topological Hochschild homology of a free polynomial algebra would be that free polynomial algebra plus the free commutative algebra generated by things in the one-up suspension of X. So this is you get a minus suspension because you're coing everything in some sense. So this is sort of the analog of the HKR theorem for free polynomial algebras, for free commutative algebras, in the coalgebra case. So for co-free, co-commutative coalgebras, we get this result. In the non-graded case, this is due to Farinati and Solitar. You might notice I've restricted here to bounded chain complexes. And I've made this restriction because, in fact, there are some sneaky issues about products versus coproducts that come up when you try and understand the totalization. So in particular, I mentioned there are like many bodies buried in totalization. One of the bodies is forcing me to have a boundedness restriction here. OK, so let's talk about spectra. So in spectra, this gets trickier. Maybe you're not surprised about that. So in spectra, this gets trickier. Maybe two reasons I might highlight why it gets trickier. One is that there's bodies in tote. They're still there, and maybe they're worse. So tote is harder to understand. And in the case where we were working sort of purely in algebra, we have this pleasant coincidence that for, say, abelian groups, finite products and finite coproducts agree. This is not the case in spectra. It's the case up to equivalence, but you should maybe take those equivalences seriously. So product and wedge are equivalent, but they're not actually equal. And so you have to be careful about the fact that they're not actually equal at some point. So that complicates life. So I'm going to tell you, in spectra, things are more complicated. And so we don't have sort of the strict analog of this result in the world of spectra. I can't just say, cross out DG modules, put in spectra, voila. What I can say, though, is that we have an analog of this result at the level of homology. So we have a homological analog here. So what does it say? Let's say if C is a co-commutative coalgebra spectrum, I want it to be cofibrant for that nice homotopy invariance property. And maybe I should say cofibrant, I mean cofibrant as a spectrum. So far as I know, there's not a good model structure on coalgebra spectra. In fact, all the tricks that you use for getting a good model structure on algebra spectra, they don't really go through. This is related to totalization being bad and not doing things like commuting with smash product, which geometric realization does do. So I mean cofibrant is a spectrum here. So this is a cofibrant, and if it's homology coalgebra, right, so every space gets to have a cohomology algebra, so it gets to have a dual homology coalgebra, so whose homology coalgebra is, well, I want to say it's going to be co-free, but let's be more precise about that, is So the homology coalgebra of C, coefficients in our field, is going to be divided power algebra, by which I mean the underlying coalgebra structure of the divided power algebra on a bunch of classes, x1, x2, et cetera, where the xi, these cogenerators, are an even degree and non-negative degree. And only finitely many cogenerators in each individual degree. All right, so if I have a co-commutative coalgebra spectrum that I know has this nice form of its homology coalgebra, so it's co-free to the eyes of homology, then I can say what the homology of its CoTHH is. So that's the sense in which I have a homology level analog of this theorem right here. This is not where I say what this is, apparently. This is where I say it. So then the homology of CoTHH of my coalgebra spectrum with FP coefficients. What does this look like? Well, it looks like the same thing again, the divided power algebra on my same classes. And then I tensor with the exterior algebra on a bunch of other classes, Z1, Z2, et cetera, where here the Zi is in degree, the degree of xi minus 1. So what you should be thinking is this was my free co-commutative coalgebra on a bunch of things that live in even degrees, and then I took their shifts down, and I took the free co-free co-commutative coalgebra on those guys, and I have the tensor product of those two things. So you should think this is like SC of x, and this is like SC of the desuspension of x. So this is how this result works. And this is the sense in which it's the homology level analog of this result here. So let me say a word or two about where this comes from. So this is the result, this computation, this is the result of a spectral sequence that we construct. Which we call the co-Buchstedt spectral sequence, because it's dual to the Buchstedt spectral sequence. So what does it look like? Well, it starts from the co-Hochschild homology of the starts from the co-Hochschild homology of the homology of C. So so E2 is going to look like the co-Hochschild homology of the homology of C. Let's have our coefficients be implicit, and it wants to converge to, like it wishes it were converging to, the homology of CoTHH of C. And you'll notice I'm being a little wishy-washy about this convergence because this is an instance of the Bausfield conspectral sequence for a cosimplicial object, and Bausfield conspectral sequences don't just get to converge just like that. That's not how they go. So we prove that under nice conditions, you get complete convergence here. In particular, this applies when you have a suspension spectrum. You'll get convergence results there. So that's good. That's telling you that maybe you have some access to this guy that I claim we've computed. And in fact, if you work quite hard at understanding Bausfield and Kahn, you can show that in the case where, so this is true for just C, a coalgebra spectrum. Let's draw a little box here. If C is co-commutative, you can delve back into the depths of Bausfield and Kahn, and you can figure out that this is going to be this is a spectral sequence of coalgebras. Just like if you have a commutative algebra, then the Buchstedt spectral sequence gets to be a spectral sequence of algebras. So you have a spectral sequence of coalgebras. And this means that, in particular, the differential satisfies a co-Leibniz rule. And so the co-Leibniz rule in this particular case, where all your generators are hanging out in even degrees and whatnot, it's going to force a collapse result. So forces collapse in our case. So this is forcing collapsing because of the co-freeness, the co-generators, and the even degrees. And so really what you should think is that what we're computing as the homology of the CoTHH of my co-commutative coalgebra, this is actually, my goodness, this is actually like what you would get in the E2 page. This is the co-Hochschild homology of this coalgebra way over here. This is its co-Hochschild homology, and so this spectral sequence is collapsing, and you can tell what's going on there. So, I feel a little silly. So I hung out at Northwestern for 4 years, right? And hanging out at Northwestern for 4 years means that you get to see a lot of people do a lot of really excellent calculations. I think this is a fair statement. And with spectral sequences, and I was like, man, I wish I had some spectral sequences and I could compute some stuff with them. And look, I did, but maybe that was not the most exciting computation to make. But here's our spectral sequence, and this is perhaps your favorite kind of spectral sequence computation because it works. All right, so maybe I should just tell you like one kind of example to sort of go back to the beginning. We talked about how spaces were going to give us examples of coalgebras. And so perhaps one kind of space you might want to think about is we could look at BUN. So in particular, our result is going to tell us that we're going to be able to see that the homology of CoTHH of the suspension spectrum of BUN with FP coefficients, we'll make them less implicit again. So what is this going to look like? It's going to be a polynomial algebra, divided power algebra, on a bunch of classes y1 through yn, living in degrees like 2, 4, 6, 8, etc. So degree of yi is 2i. And then tensor with an exterior algebra, the underlying coalgebra of an exterior algebra on the desuspension of these classes. That's totally a 1, and that's an n. And then these guys have degree of yi minus 1. So, I've told you at the beginning that this thing was actually going to be computing the same thing as the homology of the free loop space, which is a thing that we know how to do. But in this case, because we're seeing that the homology of BUN is a co-free algebra, we're getting this result sort of very immediately. It's falling from this collapse. And this is a sort of a more accessible object from the coalgebra perspective. And in fact, you can do this sort of for a whole bunch of the Lie groups and things like that. The idea is that coalgebras might be smaller than the algebra computations in some cases. So that's one particular example where this theorem is maybe not telling you something new, but telling you a new way to think about something that you did know. And I think I'll stop there. So Nito is asking whether this works for comodules over coalgebras. Probably. We haven't actually worked that out yet. I should say that this is work with Gerhard and Hogenhaven and Shipley and Ziegenhagen, and really there's a lot of stuff that we're pushing to the future. And in fact, I have conveniently pushed a lot of interesting questions to Brooke's talk on Friday, where she will tell us some interesting answers to some interesting questions that you might think about. So in particular, I don't actually know. This is something we're interested in exploring.
If you look at the Bohmann spectrum of any vector bundle over space, that is a natural structure. Do you have what you expect to be the answer if that thing did work? Do you have a sense for what you want the answer to be?
I actually haven't thought about that case, but I'd be interested to talk about it. Tyler.
Is there something that's dual to like circle action on CoTHH?
This is another excellent question that I wish I knew the answer to. So I think we suspect that there should be some sort of analogous to the circle action, some sort of analogous action. We haven't sorted out those details yet. Yeah.
In the co-commutative case, you get something like using an enrichment of a simplicial sets or something, like tensoring with this one like topological motion homology, sort of dualizing this to this context?
So I guess the question is, can we think about this as cotensor with S1? So at the level of cosimplicial objects, this is what this certainly looks like. If you're just thinking about, I have a nice simplicial set, S1, and I want to like take the cosimplicial object I should get by cotensoring with it, that's exactly the cosimplicial object that I wrote down for you in this case. Understanding how the totalization behaves with respect to that idea is not clear. And in particular, if I had a nice model category of coalgebra spectra, then yes, that would be the case, that in the for a co-commutative coalgebra, this would be like cotensor with S1. But since I haven't got that model structure, I can't commit at that level. But that's certainly what it wants to be. And perhaps the problem is that this model structure, at least based on the things that we know, this is not going to happen this way. And so we have alternate possibilities, like what if you had a totally different model structure on the category of spectra? Well, that seems hard. So maybe you should move away from model structures and start thinking about some sort of infinity categorical structure and deal with your homotopy coherence thingies in that context. And either of those things would hopefully make what you're suggesting true. Not right now, I can't.